Good morning, chemistry students. It's our Friday, and we are going to finish Module 13 today. And for homework, you will have a test. I'll send you pictures of that over text message. I'll also post it on Homeschool Minder. So I'm going to put that there. And if you have any questions about your test, I know it's a little bit more difficult to do it by yourself. So just reach out to me. I'll be happy to help you, and you're welcome to use your book and your notes and any of these videos that are helpful to you. Just please don't use the internet for your test. So I'm gonna go ahead and jump in and finish the module for you today. Like I said, just reach out if you have any questions about anything. And we are gonna go ahead and get started with class. So I'm starting on page 475. And yesterday we talked about entropy. And today we're going to kind of talk a little bit more about that. So first, we are going to, let's see, did we talk about the second law? Yeah, we talked about the second law of thermodynamics yesterday as well, as relating to entropy. The entropy in the universe must always increase or remain the same. It can never decrease. So they kind of start this section out with an interesting thing, and I might come back to it and spend a little bit more time on it at the end if we have time. But you would think that the second law of thermodynamics makes evolution impossible because you're going from simple life forms, which are technically disordered, to evolving into ordered life forms. You would think that the second law would prove that this can't happen. And although you would like to be able to prove that, that's not true. There are spontaneous processes that occur every day that result in a decrease in disorder, which you would think violates the law, but we'll talk about that in a minute. So for example, say you leave a bucket of water outside in the cold and it freezes. So as we learned earlier, the solid state of matter has a lower entropy than the liquid state. So that would mean that the water went from a state of higher entropy to lower entropy. So it looks like it's decreasing, and that seems to violate the law. But we're only considering part of the process here. So we're going to kind of go more into detail about the rest of what that is affecting. So the energy that the water lost when it turned into the solid state, where did it go? It was released into the surroundings. So as a result, when water freezes, its surroundings heat up a little bit. And this might seem odd, but it is true. The very process of freezing requires a release of energy. So what happens to a substance's entropy when it heats up? The entropy increases, just like we talked about. So the surroundings of the water, the entropy in the surroundings increased, even though the entropy of the water decreased. So that offsets each other. And as a result, the change in entropy of the universe did not change. And remember, it can increase or remain equal to zero. So in this example, it stayed equal to zero. They balanced they canceled each other out. So we have to look at everything that's affected, not just the substance that we're looking at. So this includes the system that we're interested in and all of its surroundings. So let's just do a real life example. Suppose that you're sitting at home and your house is a mess, or your room, and you decide to go clean it up. So you begin to transform it from a high entropy state of mess and disorder, and you transform it into a lower state of entropy where it's neat and tidy and organized. This is a lower state of disorder. At first glance, you would think that that violates the second law of thermodynamics, but remember what we just talked about, we have to talk about the surroundings. So what did it affect? Well, when you got up and started moving, that agitated the molecules that make up the air, causing them to move faster, and this increased the entropy of the air molecules. And plus, as you began to clean, your body was burning calories to supply you with energy. So this causes your body to heat up, which increases your body's entropy. So the air in your body, entropy increased, even though in your room or your house, the entropy decreased. So as you can see, there's a balance there. So, well, there is a way to measure the exact entropy that changes in a chemical reaction. So we've already determined how to find the change in entropy of the reaction, but we need to determine the effect that the reaction is having on its surroundings. Sorry, I kind of said that in a jumbled way, but basically we've learned how to measure the reaction's entropy, and now we want to measure the surroundings of the reaction's entropy. So the main way that a chemical reaction can alter the entropy of its surroundings is through its enthalpy, its change in energy. So if a chemical reaction has a negative change in enthalpy, it releases energy into its surroundings. And as a result, if it's releasing the energy into its surroundings, the surroundings entropy is going to increase. And the opposite is also true. So say you have a positive change in energy, it's absorbing energy, the chemical reaction is taking the energy in. That means that it's taking energy from its surroundings, so the entropy of the surroundings is going to decrease because it's losing energy. So it's going to a lower state of entropy. Okay, so we need to look at change in entropy and change in enthalpy when we're trying to figure out the surroundings. So let's see. The change in enthalpy will allow us to learn about the change in entropy of the reaction surroundings. There is a simple formula for this. It relates the change in entropy to the change in enthalpy, and it's called Gibbs free energy. I'm on page 477 in your book, and this is equation 13.6. It's about halfway through the page, and that's your equation there. So the delta G, that is the Gibbs free energy. And the delta H, as you know, is change in enthalpy. And then the capital T there is the temperature of the surroundings in Kelvin. So make sure that if it's not in Kelvin, we have to convert to Kelvin if we're using this equation. And then the delta S there is change in entropy. So the Gibbs free energy can tell us whether or not a reaction is consistent with the second law of thermodynamics. So if it is, we say that the reaction is spontaneous because we know that it can proceed. Sorry, I can hear them over there. If it's not consistent with the second law, we call it not spontaneous because the reaction cannot occur. So as long as Gibbs free energy for any reaction is negative, the reaction is consistent with the second law. However, if your delta G, if your Gibbs free energy is positive, the reaction is not consistent with the second law. And they kind of give that to you there in blue at the bottom of 477. If the change in G is less than 0, it's consistent with the second law, it's spontaneous. However, if it's greater than 0, if it's positive, it cannot proceed because it violates the second law. There are ways that a reaction can affect its surroundings other than change in enthalpy. That's not the only thing that it affects. So since the equation for Gibbs free energy does not consider any other factors, it's not an exact way of determining the spontaneity of a reaction, but it's such a good approximation that chemists are content to use it. So that's all we're going to use for this module, even though it's not extensive. All right, so change in G has to be negative. Let's talk about how the change in G, the Gibbs free energy, will be negative. If the change in enthalpy is negative, your delta H, and if your delta S, change in entropy, is positive, then we'll have a negative term times a positive term, and it will always be negative. So then it says the first term will be negative and the second term will be positive. If the negative term has a positive term subtracted from it, the result will always be negative. So if a reaction is exothermic, that means it's releasing heat into its surroundings, and it has so that means it has a negative change in enthalpy, and also has a positive change in entropy, it will always be spontaneous reaction. So negative change in delta H, positive delta S will always be spontaneous. On the other hand, if delta H is positive and delta S is negative, then your Gibbs free energy will always be positive. So that means if it's endothermic and has a negative change in entropy, it will never be spontaneous. So that means we can determine without even looking at actually plugging the numbers in whether the reaction is exothermic or endothermic, and determine the sign of its change in entropy, and then we can at that point decide if it's spontaneous or not. But those aren't the only two possibilities. But if it fits one of those two criteria, you don't even have to plug your numbers in. So if it is, in summary, I know this is a lot, if it's endothermic and its delta S is negative, I'm gonna write it out for you so you can like kind of take a note. Okay, so endothermic and change in S is negative, then the reaction is not spontaneous. It will never occur. But if it's exothermic and change in S is positive, it will always be spontaneous. So just a little note for you, it's a little shortcut. If you don't know that, that's really okay, because you can always plug the numbers in. So if you want to remember that shortcut, go for it. If not, then just plug the numbers in. So now we're going to talk about that, because those are not the only two possibilities. So suppose your change in enthalpy, delta H, is negative, and your delta S, your change in entropy, is also negative. So two negatives. Then that means that sometimes you'll have a negative number subtracted from another negative number. So sometimes it'll be positive and sometimes it'll be negative. So you don't know if that one's going to be spontaneous or not. So that in that case, we would have to determine the value of Gibbs free energy to determine whether or not the reaction is spontaneous. Okay, so let's see. Because the Gibbs free energy is a state function, which we talked about earlier this module, which you need to know for your test what a state function is, we can use Hess's law. So the standard Gibbs free energies of formation is shown in table 13.5. And these are just some common substances that you would use in chemical equations, and they've already figured out for you the standard Gibbs free energies of formation. So there's your table at the bottom of 478, and there's your equation at the bottom of 478 as well, equation 13.7. And that is how you figure out the change in, or the Gibbs free energy for your equation, using if all your substances are found in this table, just like we've done earlier this module with change in enthalpy and change in entropy. Same kind of equation here. You have the summation of all your products Gibbs free energies minus the summation of all your reactants Gibbs free energies. And remember that the standard Gibbs free energy of formation of any element in its elemental form, so like hydrogen, H2, oxygen, O2, would be 0, just like it is for enthalpy. Okay, also, these are all under standard conditions, which is 298 Kelvin and 1 atmosphere of pressure. So if you're working with a reaction under different conditions, different temperature, then you're going to need to use equation 13.6, which was on page 477. So we are going to look at an example and kind of see how these equations are going to apply and how we can figure this out. So let's look at example 13.7. It's on page 479. And it says, in example 13.3, we studied the following chemical reaction. 2NO gas plus O2 gas forms 2NO2 gas, and found that its change in enthalpy standard was negative 114.2 kilojoules, if the change in entropy is negative 147 joules per Kelvin, what is the Gibbs free energy at 532 degrees Celsius, which is 805 Kelvin? Is it a spontaneous reaction at this temperature? This might sound like a lot, but it's really not that hard, I promise. Okay, so in this problem, we are working with a reaction that's at a temperature other than standard conditions, other than 298 Kelvin. So the first thing that we need to do is convert. Oh, no. We don't need to convert. Sorry, I apologize. We don't need to convert. We need to use equation 13.6, not that last one we just looked at. We're going to use the equation on page 477. And they give that to you there. But the one thing that you need to notice is that the units are not consistent because the change in enthalpy is measured in kilojoules and the change in entropy is measured in joules per Kelvin. So we need to convert the kilojoules to joules so that we can be consistent throughout the equation. All right, so negative 147, you'll see there, joules over Kelvin, and they're converting that one to kilojoules, my bad. I think you can do either or, but they're doing this one, so let's follow along. So negative 147 joules per Kelvin times 1 kilojoule is 1,000 joules equals negative 0.147 kilojoules over Kelvin. All right, so now we can use the equation. So as you see there, the equation for Gibbs free energy is the change in enthalpy minus temperature times change in entropy. So we're just plugging the values in now because they've already given them to us in the problem. So it's really easy. So you're just plugging in there the change in enthalpy, they told you was negative 114.2 kilojoules, and then minus, and then you need to put in parentheses your temperature times your change in entropy because in math you learned the order of operations. Please excuse my dear Aunt Sally. We're going to multiply before we subtract. So let's put that in parentheses so that in your calculator it's going to multiply before you subtract. So 805 Kelvin was the temperature they gave us, and it has to be in Kelvin, so we're good there. And then we're going to put in the value that we converted to, that negative 0.147 kilojoules over Kelvin. If you plug all that in the calculator, you're going to get 4 kilojoules. And notice that change in entropy has the Kelvin temperature unit in it. So let's see. Notice that the temperature we use in the equation must also be in Kelvin, which we talked about already. Since the Gibbs free energy is positive, we can say that this reaction is not spontaneous. The decrease in entropy of the reaction is not offset by the increase in entropy of the surroundings caused by the release of heat. So this reaction is not going to occur. It violates the second law of thermodynamics. Okay, so next question they ask is there any temperature at which the above reaction does become spontaneous? Since Gibbs free energy must be negative for the reaction to be spontaneous, this equation really asks for the temperature at which Gibbs free energy falls below 0. So that means you can write this equation out just like they put there at the bottom of 479. So it would be that equation for Gibbs free energy, change in enthalpy minus temperature times change in entropy, would be less than 0. And then you're just going to plug your values in from there and solve for temperature. So this is kind of tricky because it's an inequality, not a equal sign. So that means if we are multiplying or dividing both sides by a negative, then we switch the direction of the inequality sign. Hopefully you remember that from algebra. So they're going to go ahead and solve for that. And once they're finished, they're going to get that the temperature would have to be less than 777 Kelvin for the reaction to be spontaneous. Hopefully you understand that, but we're going to do an example together too. So what is Gibbs free energy for the following reaction at standard conditions? Is it spontaneous? So they give us this equation here, and it says standard conditions, so that means we can use table 13.5 and equation 13.7. So if you go back one page, page 478, that has your table and your equation right there at the bottom. So that's what you're going to be using for this one because it's under standard conditions. So we're going to look for the value of each of our products and then the value of each of our reactants and add those up and subtract from each other. So first product we have is CaCl2 solid. And if you look on the table, you will see it there. I'm looking to see if I can find it. And that's on the last one, negative 750. So there's only 1 mole of that, so that's why they put 1 mole times negative 750 kilojoules per mole. And they didn't even put in the value for H2 because hydrogen H2 is in its elemental form, which means it's just going to be 0 like we talked about. So we don't even need to write that in because it's just 0. And so we're going to subtract that's the products, minus, and then we're going to add up the reactants. So let's look at the reactants. First we have calcium in the solid form. That's going to be an elemental form as well. So that's going to be 0, so we can ignore that one. And then we have 2 moles of HCl. So they do 2 moles times, and then we're going to look on the table for HCl in aqueous form. And let's see, that is in the last column as well, and it's negative 131. So that's where they got that number. They plugged it all in, and they got negative 490 kilojoules. And that means the reaction is spontaneous because you got a negative value for Gibbs free energy. We are going to do 2 examples of this, and hopefully that'll be helpful to you on your test because there are a couple of these on your test. So let's do 13.11 and 13.10 together. It can be tricky. So I'm going to get the answers out of the book too and just make sure I'm telling you everything right and in the best way. All right, let's change to the whiteboard. Sorry. Clearing this out. All right, on your own 13.11, the first thing that I want you to do in your book, if you're looking at the question, it's everything is good. But if you look in your student book, it says the standard change in enthalpy of a certain chemical reaction is 20.0 kilojoules, and the standard change in entropy is 123 kilojoules per mole. That unit is wrong, so you need to mark out kilojoules per mole, and that's with the 123, and change to joules per Kelvin. I'm not sure why they did that in the student book and not in the textbook, but that is wrong. So go ahead and fix that, and that should help you a little bit. Okay, so it should read 123 joules over Kelvin. At what temperatures is this reaction spontaneous? So like we talked about before in the last example, your delta G, your change in your Gibbs free energy, needs to be negative for it to be spontaneous, right? So that means we're just going to, this is our original equation. Change in G is equal to change in H minus temperature times change in S. Okay, let's stretch that out a little more. Okay, so now we can set that. This is the equation for what we're trying to solve, but we need it to be negative, so we're going to set all of this to less than 0. So change in H. There's Kaysen. Hey, Kaysen.
Your time, if that's how.
Hello.
All right, let's see here. I'm on your own 13.11. And I just gave a little thing at the top. I don't know why, but in your textbook it's correct, but in your student book it's wrong. There in the problem on 13.11 where it says 123 kilojoules per mole, mark out that unit and change it to joules over Kelvin. All right, so moving on, we just talked about how your Gibbs free energy needs to be negative for this to be spontaneous. So we're setting our equation for Gibbs free energy equal to 0, or less than 0, sorry. Okay, times changing this. And then let's see if I can find that. There we go. Would have to be less than 0. All right, so first of all, before we can get started, we need to convert, because we have kilojoules and then we have joules over Kelvin. So we are going to convert the joules over Kelvin. So that's the change in entropy, 123 joules over Kelvin. And we're going to just use a conversion factor. So times 1 kilojoule over 1,000 joules. And that's going to give us 0.123 kilojoules over Kelvin. So now our units are consistent, and we can go ahead and plug our numbers into this equation right here. All right, so they gave me the standard change in enthalpy was 20.0 kilojoules minus, and we're solving for T, so I'm just going to put T. And let's put this, okay, times, and I'm plugging in the number I just converted there. That was our standard change in entropy, 0.123 kilojoules per over Kelvin. And that's going to be less than 0. All right, so let's see. The first thing that we're going to do is, it looks like, I'm looking to see if they did the same thing I did. They subtracted the 20 kilojoules first from this side. So I'm just going to kind of go underneath. So we're subtracting the 20 kilojoules from this side. And that means we also have to subtract it from the 0 side. Okay, 20 kilojoules. All right, which is going to give us negative T times 0.123 kilojoules over Kelvin is less than negative 20.0 kilojoules. Okay. Next, it looks like they divided by negative 0.123 to get rid of this negative sign and to move this to the other side, so T would just be all by itself and not be negative. Okay, so we're dividing by, I'm going to have to draw a line underneath this to help you see. We're dividing on this side of the inequality and dividing on this side of the inequality. So we're dividing by negative 0.123 kilojoules over Kelvin. Also on this side, dividing by negative 0.123 kilojoules over Kelvin. Okay, when you do that, you'll see your negative sign here with the T is going to cancel. And then your 0.123 is going to cancel, leaving T by itself over here. Okay, and because we divided by a negative number, and this is an inequality, that means I'm going to have to flip the inequality the other way. So now what our new equation looks like is T is greater than negative 20.0 kilojoules divided by negative 0.123 kilojoules over Kelvin. And as you can see here, kilojoules is going to cancel because it's on the top and the bottom, and we'll just be left with the unit of Kelvin. So we're going to put this in the calculator as negative 20 divided by, I don't know what happened here. Why does that say 10? It should be, I'm sorry. I need to fix that. I'm sorry, I must have plugged a or typed a wrong number. So let me fix this. T is greater than negative 20.0 kilojoules divided by negative 0.123, there we go, kilojoules over Kelvin. Okay, and your kilojoules are still canceling, so you're plugging in the calculator negative 20 divided by negative 0.123. So when you do that, you'll get that your temperature must be greater than 163 Kelvin. Let me plug it in the calculator and see the exact number you get and see what they're rounding to. So negative 20 divided by negative 0.123. I got 162.601626. So we're rounding to 3 because we have 3 significant figures here. So if your temperature was greater than 163 Kelvin, then that means the reaction would be spontaneous. Okay, that is on your own 13.11. Now we are going to do on your own 13.12. So I'm going to clear this out. All right, on your own 13.12. Last one. So it says, is the following synthesis of ethyl alcohol a spontaneous reaction at 298 Kelvin? And it gives us an equation. Well, at 298 Kelvin, that's standard temperature, standard conditions. So we are able to use that other equation, which is on page 479, and no, 478, sorry, the bottom. And as long as all of our substances are on the table. And I feel sure that they probably are. So we're using equation 13.7, and it says that your Gibbs free energy standard is equal to the summation of, I'm not going to write it out because it's hard to do with typing because it's all these symbols, but the summation of your products minus the summation of your reactants. So let's go ahead and plug that in. So we have our first product is C2H6O liquid form, and we're going to look for that on our table here, table 13.5 on page 478. And I see it there on the last one at the top. It's negative 175. There's 1 mole of this. Okay. 1 mole of this times negative 175. And the units that they're using is kilojoules per mole. Okay, now my other, I'm gonna have to do another set of parentheses here because I have another product. So I'm gonna add that, whoops, add that to my other product, which is H2O liquid form. And I see that in the table. Notice there is H2O in the liquid form and in the gas form in your table, so make sure you look at the right one. So in the liquid form, its standard Gibbs free energy of formation is going to be negative 237. Now in the equation, we only have 1 mole of H2O. So 1 mole times negative 237 kilojoules per mole. Okay. That is all of my products, so I can close my big bracket of parentheses. And now I'm subtracting. Now I'm going to start a new bracket because I have my reactants. First reactant is 2 moles. So I'm going to go ahead and write that. 2 moles times, and then I need to find the value for CH4 in the gas form. That's going to be the first one on your table, negative 50.8. Negative 50.8 kilojoules per mole. Okay, now I would be adding this to my second reactant, but my second reactant is oxygen, O2, in the gas form, which is its elemental form. So the value of that is just going to be 0. So I really don't need to include it. So I'm going to close the brackets. This is what it's going to look like in your calculator. I'm going to ignore the 1 moles because it doesn't affect the value in any way. So in my calculator bracket, or parentheses, negative 175 plus negative 237. Like I said, I'm ignoring the 1 because 1 times this is just this. So I'm ignoring the 1. I'm going to close my parentheses, minus parentheses 2 times negative 50.8. Pay attention to your negative signs. Don't forget those. They're very important. So let's put that in the calculator. Negative 175 plus negative 237 minus 2 in parentheses times negative 50.8. Okay, I got negative 310.4, and my unit is going to be kilojoules because the moles are canceling. And that is a negative value, so that means that to answer their question, yes, it is a spontaneously occurring reaction. So our answer would be yes, since it's negative. All right, and that is all we had for today. For homework, I said at the beginning it's going to be the test for Module 13. I'll send out the pictures for it over text message, and it'll be on Homeschool Minder. If you have any questions, just feel free to reach out to me, and I'll take those on Monday, and then we'll go ahead and start on Module 14 and try to kind of make it through that module by the end of the year. So that's all I had. Any questions before I head out? All right.
Yep.
Well, have a great weekend, and let me know if you need help on your test. I'll send it out here in a few minutes.
You too. Bye.
Bye, Kason.